In today's webinar, we'll be covering how you can use Gurobi and Anaconda together to more easily develop optimization models and then turn them into powerful Python applications. Today's webinar will be a joint presentation by Gurobi Optimization, the makers of the leading math programming solver, and Continuum Analytics, developer of Anaconda, the leading open source analytics platform powered by Python. Now I'd like to introduce you to our two presenters today. Our first presenter is Dr. Renan Garcia. He is an optimization support engineer at Gurobi, received his PhD from Georgia Tech, has over a decade of experience implementing decision support systems, and is an expert in optimization modeling and software development. Our second presenter is Dr. Michael Grant. He is a senior solutions architect at Continuum Analytics, received his PhD from Stanford University, is the developer of the CVX modeling framework, and is an expert in nonlinear convex optimization. With that, thank you for joining us again today, and here's Dr. Renan Garcia.
Thanks, Chris. Before we dive in, I'd like to go over the agenda for the webinar. We'll begin with a proposition about how the combination of Gurobi and Anaconda offers a complete solution for developers of optimization and prescriptive analytics models. Then I'll introduce Gurobi Optimization and our state-of-the-art math programming solver. At that point, I'll turn it over to Dr. Grant, and he'll give you an overview of Continuum Analytics along with their Anaconda platform. After that, I'll go over the Gurobi-Python module and walk you through a simple MIP example while demoing the Spyder IDE distributed with Anaconda. Then Dr. Grant will take you through a rich portfolio optimization application while highlighting some very useful tools that are distributed with Anaconda, including Jupyter Notebooks, Pandas for data analysis, and Bokeh for visualizations. Then we'll conclude the webinar with some final thoughts. Okay, let's begin with the proposition. In case you're unfamiliar with Python, it's a powerful, high-level programming language which is critical to enabling the Gurobi-Anaconda combination. Gurobi has developed a Python module that brings the intuitive feel of a modeling language to Python, while the Anaconda platform, which is powered by Python, delivers a full application development stack, as well as an interactive environment for data analysis and modeling. Therefore, together, they provide a complete solution for those looking to build optimization applications. The great thing about Python, though, is it's one of the easiest programming languages to learn for non-programmers. And this enables collaboration between software developers and analysts. The idea is the analyst, which may not be a great programmer but is mathematically inclined, can get up to speed quickly and prototype an optimization model with relative ease. Moreover, they can use the interactive tools distributed with Anaconda, like Jupyter, to validate that model. Then, once they are satisfied, they can hand the prototype over to a software developer for integration, and there's no need to port the code at all because they're working in the same tools, which is Python. In case you're unfamiliar with Gurobi, let me give you the quick tour. Gurobi Optimizer is a state-of-the-art math programming solver and includes algorithms for both continuous and discrete optimization problems. For the continuous problems, Gurobi offers primal and dual simplex algorithms, along with a barrier method, which is a parallel interior point algorithm. For discrete problems, Gurobi offers a parallel branch and bound algorithm in which the relaxations are solved with continuous algorithms. All of the libraries are built with the latest CPU instruction sets, and the parallel algorithms are designed from the ground up to take advantage of today's multi-core CPUs. Of course, there's other algorithms included, such as pre-solve, which is designed to reduce the problem sizes and strengthen the formulation. We have parameter tuning tools, which look for the best parameter settings to customize your algorithms. And we have tools that help you determine infeasibilities in your model, like irreducible inconsistent subsystems. What's key is that Gurobi lets you work however you prefer. You can either use standalone tools such as the command line interface and a full-featured interactive shell, which is essentially a Python shell with extensions for Gurobi, or you can use your favorite programming language to embed Gurobi within your own applications. And we have matrix-oriented APIs such as C, MATLAB, and R, and we also have object-oriented APIs such as the Python, C++, Java, and .NET. Before you can solve an optimization problem with Gurobi, though, you must be able to specify it in the form of a model. And what I'm showing here is a generic optimization model that can be solved by Gurobi. Of course, the first thing you need to do is specify the decision variables x. that represent the choices that you're going to make in your model. You have an objective function, which could be linear or quadratic, and it's used to rank solutions for your model. And then you have the constraints, which restrict the possible values for decision variables in the feasible solutions to your model. There's a broad range of network constraint types. You can have things like linear constraints, variable bounds, quadratic constraints, which are used a lot with risk, which Dr. Grant will show later on. And I don't intend to walk you through each of these in great detail, but I do want to stress that this is a very powerful modeling framework. In particular, the integrality constraints, which allow you to model logical conditions and very complex constraints. Gurobi has over 1,200 customers in nearly 24 industries, so this is not something that's limited by power and flexibility, right? It's flexible enough to be used in diverse applications such as scheduling the NFL, to routing aircraft, to even medical applications like cancer treatment plans. Of course, many of these components are optional. The most common model we see is a mixed integer program, or MIP, which involves a linear objective function and linear constraints. It might have variable bounds, but it does have integrality restrictions on some or all of the variables. Note that MIPs are relatively easy to formulate, but they are NP-hard in general, and even reasonably sized problems are very challenging to solve. I know that some of you joined us today are coming from the open source world of Python, and there are open source solvers out there. However, we often get approached by prospective users who have initially prototyped models with these solvers, but ran into issues once they ramp up their problem sizes. To give you a sense of how Gurobi compares to some of these open source solvers, I've included results here from industry standard public benchmark tests. These are maintained independently by Hans Mittelman at Arizona State University, and he runs the competitive benchmark experiments himself. This particular table is based on the MIPLib 2010 test set with runs limited to a single processor, which is appropriate since some of these solvers don't support parallelism. The ratios in the columns indicate how much faster Gurobi is when compared to a given solver. And I don't want to spend too much time on this, but the main takeaway is that Gurobi's performance advantage over these solvers is significant and only improving over time. Moreover, some of the most widely used solvers like GLPK and LPsolve were dropped by Hans a while ago because they were no longer competitive enough. Feel free to visit Hans' website and you'll see that Gurobi is also the leader amongst commercial solvers as well. So what are some other reasons to choose Gurobi? I mentioned performance leader here again because I want to stress that we're not going to stand still. So there's an average 2x improvement with each major release, which means even if you don't do anything to your application, you're going to get a performance boost every once in a while. And over the last 6 years, this has amounted to almost a 50x improvement on the code. We have a consistent track record of innovation. We were the first to have a cloud offering. We have remote computing with client server support. We offer distributed algorithms to leverage multiple computers to solve very difficult problems. We have outstanding support with direct access to PhD level optimization experts. And we have a no surprises commercial offering with flexible licensing and transparent pricing. And finally, we have a strong academic offering with free full-featured academic licenses and a Take Gurobi With You program that allows you to take Gurobi to your first job in the first year. At this point, I'd like to turn it over to Dr. Grant so that he can introduce you to Continuum and Anaconda.
So let me tell you a little bit about my company, Continuum Analytics, and Anaconda, the product that we're offering. Continuum Analytics is devoted to the development, support, and promotion of the Python ecosystem with a particular focus on data science and big data analytics. It was founded in 2012 by Travis Oliphant and Peter Wang, two well-known figures in the Python open source community. For instance, Travis was the primary developer of NumPy and a founding contributor of SciPy. Peter Wang created the PyData conference series. On our team, we have a number of the key contributors to a variety of the best-known packages in Python, including PyTables, Pandas, Jupyter, and IPython, which we're going to be taking a look at in a little bit, the Matplotlib and visualization library. And we have created and developed a number of new projects that are rapidly rising in popularity, including Blaze, Numba, and Conda, which we are going to be talking about in a little bit. Our commercial efforts include enterprise software and support, so sometimes a larger organization organizations need more assistance than the open source community can provide, and we are there to do that. We offer training. So if you need to learn more about Python, you can do that with us. We have special courses tailored towards science and towards the finance industry. And we do consulting. So people hire us to build custom software with a heavy emphasis on computation and analytics, of course, leveraging our tools and our Python expertise. If you need assistance in any of these areas, of course, we encourage you to get in touch with us after this webinar. This is a slide that we use in a variety of contexts to talk about the fact that Anaconda, as powered by Python, is truly well suited to assist people at all levels of the software development cycle. Of course, for this particular webinar, we're probably focusing on the data scientist, the business analyst. What do we mean by that? We mean by folks who perhaps are stronger in the mathematics and the computation and the modeling than they may be in hardcore programming, and people who would prefer the ability to do interactive development and modeling over the more traditional programming approach. And what we want to get across is two things. First of all, that Anaconda, especially with the Jupyter notebooks we're going to see later, is very well suited for this type of interactive modeling and development. At the same time, by doing that development in Python, your final work product is Python code that the other developers in your organization will be ready to integrate into applications. And so, again, bringing modeling and development together should make collaboration significantly smoother for everybody. But it's a fair question to ask, why Python? So let me offer a couple of bullet points here. First of all, it's designed to be a very readable language with its indentation convention, or indentation requirements rather, and its comments and documentation string conventions. It supports a variety of programming styles, and it has a rich standard library. I really enjoy being able to use lists and tuples and dictionaries within Python without having to import another library. But I would say that probably one of the most important features of what makes Python such a useful language is its incredible community library, this outstanding library of open source packages for just about any need in the Python space. It really is incredible just how much you can draw from the work of other people. These libraries are mature and well documented and stable and developed in the open. Great stuff. There's great online documentation and online support communities, and of course the name is pretty nice too. Now, Peter Wang, our CTO, calls Python the second best language for everything, and I think that's really kind of humorous at first glance, but it's also very serious. So, for example, when I'm doing computational work, I often like to work in MATLAB. In my view, it's one of the more intuitive choices there. But Python is actually quite strong in that area as well. And it's also strong in a variety of other areas where MATLAB is particularly weak. And so when you're building a full stack application, having a language like Python that is strong in so many of different areas makes it an obvious choice. Let's talk about the Anaconda Python distribution. We would strongly, of course, encourage you to use our Python distribution. It is, in my estimation, and I believe this to be true before I joined Continuum myself, that it's the easiest to install Python distribution with a particular focus on data science and data analytics. It runs on Windows, Mac, and Linux, 32-bit, 64-bit. You can choose between Python 2 and 3. It's your choice, although we always encourage people who are building new projects in Python to start with 3.5, actually, I believe is the latest version. When you install Anaconda, you get 150 packages, the most popular packages for data science, and they're. But if that's not enough, then we have the Conda package and management system built into Anaconda. Another 350 packages are available with a simple Conda install command. And the environment management lets you create isolated silos for multiple projects. This is an extremely useful tool for me as a client-facing consultant when I'm working on projects. Say one project needs Python 2, another project needs Python 3, another project has a unique set of dependencies, and I want to make sure that each of these environments is isolated from each other so that I don't accidentally mix code from different projects together. The Conda environment management is extremely useful for me. If you like R, Anaconda allows you to install that as well. You can use that as your primary modeling environment, or you can work with Python and R together and pass data back and forth between them. I talked about Conda package management. This is, in order to use it, you pull up a terminal window, a command prompt in Windows, and the commands are pretty intuitive. For example, if I want to install pandas and a particular version of NumPy, I can just use a simple Conda install command. I can use it to update packages to a later version. I can list the packages that are currently installed in my environment. I can search for a package on our repository, and of course I can remove packages. All of these are simple one-line commands. Similarly, we have simple commands for creating these isolated environments or silos. So for example, in this first command, I've got a new project. I want to install the standard set of Anaconda analytics packages, plus I need Gurobi. So with this conda create command, I'm installing Anaconda and Gurobi, and Conda takes the responsibility of making sure that the version of Gurobi that I'm installing is compatible with the version of Anaconda that I'm installing, and creates a full environment containing those packages. Then when it's time for me to go in and begin work in that environment, I type source activate LP project on Linux or the Mac, or just activate on Windows. Now it's a little confusing that I have to use a slightly different command on those two different operating systems, but the good news is if I accidentally type activate LP project on Linux, it will tell me. So I'm in good shape there. When I'm done, I can return to the default environment with a source deactivate command, or I can just shut down that terminal window, and when I open a new window, I'm in my default environment. And if I need to remove the project altogether, I can do that with a conda remove command. And by removing all the packages, it removes the environment as well. So again, the ability to create these project-based environments is really easy with conda. Now, how do I obtain Anaconda? Of course, we would love for you to go to our website and get it. And by default, and typically that's what our users do, but Gurobi has created for you a great web page, and the link is here, and it will be provided for you in our follow-up emails to you, which helps you identify the exact version of Anaconda to download, and it gives you instructions on how to install the Gurobi-Python module in that Anaconda environment, and to make sure that your Gurobi license is properly set up. So, normally you would download it from Continuum, of course, but Gurobi's download page is fantastic. We would encourage everyone on this webinar to go check that out. And again, this ensures that you get the right version of Anaconda to be up and running with Anaconda and Gurobi together.
Thank you, Dr. Grant. Okay, now that we've introduced Anaconda, I'd like to cover the basics of the Gurobi-Python module. When building models with Gurobi, users typically go with one of two options. Either they use a modeling language or a full programming language. The modeling language option makes it easy to build models because the modeling constructs are built right into the language itself. And this makes for natural syntax. You can use Gurobi with several third-party modeling languages. For example, in the commercial space, you have alternatives like AMPL and GAMS, but there's also open source alternatives like CVX, Pulp, and Pioma. Since the learning curve is not steep for these tools, they're an attractive choice for non-programmers. The programming language option, on the other hand, provides for a more powerful and flexible development environment. Not only does the language have a richer feature set, but it gives you complete access to all of the solver functionality. For example, some of our users like to use callback functions for finer grained control of the algorithm, and that's not possible with modeling languages. The programming language is the natural choice when deploying models and or integrating them into applications, because these applications are typically written in those programming languages, right? So it's easier to plug the solver in. Of course, these two options suggest a natural trade-off between easy and powerful. I feel our users don't need to make that choice. In order to combine the expressiveness of a modeling language with the power of a programming language, what Gurobi has done is embedded high-level optimization constructs into the Python programming language. We had several design goals in mind for this. The first is to require minimal programming skills to get started, right? We wanted the novice user to be able to be doing useful things quickly. We wanted to bring the feel of a modeling language to the Python interface with natural syntax. And this allows for code that is easy to write and maintain. A unified design across all of our interfaces was also important to us. And we get users constantly telling us how easy it is to migrate between our APIs because there's a consistent feel. For example, the concept of attributes is pervasive in those designs. All of these APIs are thin layers on top of a native C code, right? So we really wanted to remain lightweight and efficient when compared to running the solver alone. And we wanted these APIs to consume as little memory and CPU cycles as possible. And finally, we wanted to support all solver programming needs. In this scenario, you'd have the entire Python ecosystem at your disposal, including powerful platforms like Anaconda, which will increase your productivity. If there's functionality a user needs, chances are there's an existing Python module that enables them. So let's introduce some of the essential constructs you should be familiar with in order to get started. When you think of an optimization model, the three components I mentioned earlier are typically what come to mind. You have decision variables, an objective function, and constraints. And there are objects in this interface to represent those components. You have the model object for a general model, but you also have var and const objects which represent individual variables and constraints in those models. But models are also built with lower level constructs. For example, you need arithmetic operators like addition and multiplication to build linear and quadratic expressions involving variable objects. And you need constraint operators like less than or equal to relate those expressions. So what we've done is overloaded the typical, and that gives syntax that's readable and resembles the underlying algebra. We've also added an aggregate sum operator called quicksum, which is a direct replacement for Python's built-in sum function for collections. However, it's more efficient than sum when working with collections of Gurobi var objects. And with the exception of a few other constructs, that's really all you need to know about the Gurobi module. The rest of the features are provided by Gurobi itself. There's collections like lists, tuples, and dictionaries, and these are extremely useful when representing index sets, subscripts, and data coefficients you might need for a model. Normally, we think of for-all operators as mathematical constructs, but when modeling on a computer, you need to think of them as programming operators, and Python provides loops and generate expressions for that. The end is a code that's algebraic in nature, and just to illustrate that, I've provided a simple example. On the left-hand side, I have a mathematical representation of a set of constraints in which you include a constraint xi plus yi less than or equal to 5 for all I in some index set I. And although I haven't explained the interface syntax yet, I mean, you can still gather what's going on in the code on the right because it's concise and it looks like the math. You see it tells you for all I in I, I'm going to add a constraint, and the constraint looks algebraic. To build a Gurobi model from scratch using the essential constructs I just mentioned, you typically follow 6 basic steps. The first step is to create an empty model using the model constructor. And this constructor returns a model object, which in this case we've stored in a variable called m, but we could have used a different variable name like n, and that's convenient when you're working with multiple models. Since m is an object, you can act upon it by calling methods. And that's precisely what's done in the next step when adding variables to the model. The add var method for a model adds a decision variable and returns a reference to the var object associated with that variable. Note that Gurobi uses a lazy update scheme in which pending changes to the model are placed in a queue and processed in batches. And this is done for efficiency so that underlying matrices aren't reallocated with every method call. However, this requires you to call an update method whenever necessary in order to reference these new elements. In this case, we're going to need to call the model update method only once, and that's after all the variables have been added. And that's so we can use those variables to build the objective and the constraints. And after that, the next step is to call the set objective method for that model to specify the objective function. And similarly, you'd call the add const method for each new constraint that's added to the model. Finally, you would call the output, and that will commit any remaining updates and solve the model. To help you get started quickly, the Gurobi distribution includes a Python interpreter and a basic set of Python packages. However, if you want to work within other more powerful Python environments, you'll need to install the Gurobi-Python module within those environments. Fortunately, Anaconda makes it easy to do this with Conda packages. And once you've downloaded and installed both the Gurobi and Anaconda distributions, all you need to do is open a terminal or command prompt. Then you run the conda config command to add the Gurobi channel, and the conda install command to install the Gurobi package from this channel. If you've already installed your Gurobi license key, that's all there is to it, and you're ready to use Gurobi with Anaconda. If you don't already have a Gurobi license, you should contact Gurobi to request one, either commercial or academic. Once you're issued the license, you install it on that machine with the Gurobi get key command, and to test the license, you open a Python shell and use the import statement to import the Gurobi-Python module as shown there. If everything is fine, this should execute with no errors, and you're ready to go. At this point, I'd like to walk you through a simple MIP example while demonstrating Spyder, which is distributed with Anaconda. Spyder stands for Scientific Python Development Environment. It's essentially an integrated development environment for Python developers, or an IDE, which allows you to edit and execute code all within the same tool. This interface should be familiar to those accustomed to working in MATLAB or some of the other common IDEs such as Visual Studio. The built-in editor includes convenient features such as syntax highlighting and code completion. It also has a file explorer and a documentation browser, a graphical interface for debugging based on the IPython debugger, and the IPython console allows for interactive code execution. So let's now show you what that looks like. I have Spyder open already, and I'll start with the interactive console, which allows us to run Python commands. I can do things like x equals 1 or y equals x plus 1, right? What's a convenient feature is the variable explorers, which can allow you to inspect all of the variables you have defined currently. In this case, you'll see x and y. We can use the file explorer to work with source files, right? And in this case, I'm going to open a file called simple.py. You'll see the code is now shown in an editor on the left, and it has the appropriate syntax highlighting. I can run it with the play button, and you see all the results appear down in the console. You see we found an optimal solution very quickly, and the values for each of those variables. So the first thing I do in any script with the Gurobi interface is import the Gurobi-Py module. And after this, I follow the 6 basic steps I showed earlier to create a simple MIP with 3 variables and 2 constraints. And note in this case, I've used the advar arguments to specify that my 3 variables, in this case x, y, and z, should be 0, 1 binaries. And I've also specified explicit variable names, which is useful when you're debugging and analyzing results. And sometimes you forget what these methods are, or what the arguments are that should be passed to them, right? But that's a very convenient feature in Spyder where you can type in method names. And what's great is the Gurobi documentation is included in the code itself, so it's self-documenting, right? You can find out that there's arguments for lower bounds, etc. Another nice feature in Spyder is that you can set breakpoints, and in this case, I've set one right before printing the final solution. So if I run the debugger, I can actually inspect variables in the middle of the run, right? So I can look at what the value is. I can check the lower bound and the upper bounds for the variables to make sure the value is correct. But it's a really nice feature for debugging your programs. At this point, I'd like to turn it over to Dr. Grant so he can take you through a richer example, at the same time introducing some of the other useful Anaconda tools.
What we'd like to do now is do some portfolio optimization. Now, for those of you who aren't familiar with portfolio optimization, I need to give you modern portfolio theory in one slide. This was an approach developed first by Harry Markowitz in the 50s, and it was work that was ultimately recognized with a Nobel Prize in economics. So this is serious stuff, and yet, for people familiar with quadratic programming, I think it'll find it surprisingly accessible. The way it works is that you analyze the historical data for each stock that you're interested in, and you come up with 2 numbers, an expected return, an average return, if you will, and a level of volatility, kind of like a standard deviation, that quantifies the risk of that individual stock. And then you also need a matrix of the correlations between individual pairs of stocks. The goal of modern portfolio theory is to study the trade-offs between this measure of risk and our measure of return. So for instance, we might want to shoot for a particular target return and minimize the risk of our overall portfolio in the process. Or we can maximize the amount of return that we obtain given an upper bound on how much risk we are willing to tolerate. The good news is that those are both 2 sides of the same coin, and the most basic versions of these models are quadratic programs. And I can tell you that while the basic models are not actually used in practice, Markowitz portfolios are used in financial firms today with additional modifications and improvements in complexities. And yet most of those complexities, if not all of them, are supported by Gurobi Solver. So you can do genuine portfolio design today, the way it's done in New York, with this kind of stuff. All right, I promised it was only 1 slide, but I kind of lied because I wanted to show you the model itself in a more mathematical notation. Hopefully you can recognize that this is a quadratic program. Our optimization variable x is a vector. Each element x of I represents the amount we're going to invest in stock I. The expected return for each stock is denoted by the variable rho sub I. And the variance or the volatility or risk of that individual stock is the diagonal elements of this matrix sigma. So this matrix sigma is the objective function there, defines this quadratic function of x. The diagonal elements represent the individual risk, and the off-diagonal elements help us measure that correlation that I was talking about between stocks. We'll actually get to see that in our demo. Now, before I proceed with that demo, I just want to show you what you're going to see here. I'm going to briefly jump through the three major packages besides Gurobi, of course, that we are looking at. The notebook system that we're going to be using is called Jupyter. You may have heard of it as IPython. It's a web application for interactive data analysis, and it's a great way to build these web-based notebooks that contain live code, formatted text, equations, and visualizations, and combine them all together in one document. It's a great way to prototype new algorithms, to document experiments, and then when you're happy with your work, to share it with others. Now, it was originally called IPython, but the notebook functionality proved so useful that people have implemented kernels for it for over 50 different languages. So calling it IPython wasn't really appropriate anymore. So now Jupyter refers to the notebook technology, and then IPython remains for the Python-specific code, or the Python kernel, if you will, for the notebooks. We're also going to look at a package called Pandas. Pandas is a great package for managing, processing, and studying tabular data. So anything that you might see in an Excel spreadsheet, in a CSV file, maybe any data that you would grab from a SQL server, Pandas can manipulate that data really efficiently. It handles missing data well. You can do slicing and fancy subsetting, merges and joins like SQL, and then group by operations as well. We'll be taking a look at that in the notebook. And finally, Bokeh. We're going to use Bokeh for visualization. You may have heard of Matplotlib. That's a great plotting package in Python. Bokeh is a newer visualization package, and what it brings to the table is the ability to build interactive plots that can be embedded in static web pages. So in other words, once you've finished the computation, once you've constructed the plot, it generates HTML, CSS, and JavaScript that can be embedded into a web page and provide an interactive plotting experience, even though the Python is finished running. And in fact, you can actually build Bokeh plots in other languages, including Scala, Julia, and R. I'm going to show you some of that interactivity in this notebook, but Bokeh is the name of the package that we're going to be using for visualization. So without further ado, let's pull up our notebook. We're going to pull up Jupyter now, and just so you know that this notebook has already been uploaded to the Anaconda cloud. The link is provided here, and you're going to receive that link in an email in the future. So you can actually download this notebook. You can download the data that was used to generate these results, and if you have a Gurobi license, you can run the notebook. Okay, but let's go ahead and take a look at it live now. So I'm going to pop into Jupyter, and I'm going to put, this is a somewhat blank notebook here. I've imported some useful modules. I wanted to bring up a blank notebook briefly so that you can see how it works to start building your analyses out. So maybe I want to just generate a matrix of random numbers. Oh, sorry, syntax error there. Silly me. I've forgotten my NumPy. There we go, much better. And I can also do some plots, and I'll do that really quickly. There we go, so I can do a simple plot here, but then I can also add some annotation to my notebook. So I'm going to go up here, I'm going to create a text cell, I'm going to say this is a notebook to do some computations. And I'm going to add, just for grins, I'm going to add a nice little equation in there as well, and you can see it render. So this is what we mean when we say that these notebooks can integrate live code, the results of your computations, and any annotation that you wish, visualizations, even equations. This is a great way to build a document that self-documents that work that you've done that you can share with others. But let's get to the actual meaty stuff. So again, I'm going to pull this up a little bit. This is our Markowitz portfolio design notebook. And just as a bit of, just so that you can see for yourself, I'm going to restart my kernel. I'm going to clear everything out, and I'm going to run the whole notebook at once. Okay? And just so you know, it's done. Everything has been built, and I'll be explaining all these things in a bit in only a few seconds. So I wanted to just give you a taste that all of this code ran very quickly, and it did about 102, 103 Gurobi models in that process, by the way. So there was a fair amount of computation involved. But what I really want you to see, I'm not going to be able to explain every single line of code as I go through this demo. What I do want you to know, though, is that there's only about 150, 155 lines of code here, and that includes some white space, and that includes some comments. What I would like you to take a note of is how much I am doing in such a small amount of code, and how I'm leveraging the power of these various modules, Gurobi, Pandas, and Bokeh, to get a heck of a lot done in a very little amount of code. So again, while I won't be able to explain every single thing I'm doing, hopefully you can appreciate that I can be very productive in just a little bit, in a small amount of time. So let's go through this. The first thing that I need to do is I need to load my data, and I've done so here. This was in a CSV file, and I've made this CSV file available to you, so you're going to be able to reproduce these results. So when I load it up, I get this nice pandas table with row and column headers. These are the normalized performance measures on a day-to-day basis for the Dow Jones Industrial Average in 2012. So for example, let me show you how to read this. That on January 10th, 2012, American Airlines rose 2.2%, Cisco rose about 1.05%, Chevron dropped about 1.2%. Okay, so that's what this data is. I like how it's presented in a nice clean tabular format. This is a lot of data, however, so I'd like to understand this data a little better. So what I'm going to do is I'm going to look at the mean return and volatility. Remember, we talked about those in the context of the Markowitz model, and we're going to look at the total return over the course of a year. Now, to compute those three quantities for every single stock in my list, I have a single line of pandas. This is line 1, and then I'm just putting some nice column headers on that and printing out the results. So in 3 lines of pandas, I get this table, which shows me that, sure, while American Airlines did well on January 10th, over the course of the year, it actually dropped a little bit. And the factor is that, well, actually, it lost 27% in 2012. On the other hand, Hewlett-Packard lost 95%. Then there's Bank of America, which grew by a factor of 23. That's not 23%. That's 23 times. So that was really the star of 2012, quite clearly. I can go a little bit further, and I can say, okay, Pandas, please give me the minimum and maximum return, the minimum maximum volatility, and also give me the stocks that achieve those extremes. And again, this is 1 line of Pandas and a couple of lines to give me some clean headers, and that's what this table gives me. Again, Bank of America blew the doors off in terms of return, but it was also the most volatile stock. In contrast, Hewlett-Packard performed the worst, and Johnson & Johnson, it turned out, was the least volatile stock in the list. So all this is great, but you know, there's no substitute for pretty pictures. So in 26 lines here of Pandas using Bokeh, what we're going to do is we're going to plot the performance of all those stocks over the course of a year, and this is the result that Bokeh gives me. Okay, I talked about this. This is a complete finished plot, but I talked about it being interactive. Python is not running at the moment, and yet I can still zoom in, and I can look at the various. I can zoom in and pan around and just kind of explore my plot, and of course I can reset so I can get back to the. Get back to the standard zoom level, and I can see quite clearly that yes, Hewlett-Packard was a dog, and Bank of America was a star, but it was also a roller coaster. If I had bought Bank of America in the middle of March, I might have been quite nervous for a month or so, but if I'd held on to it, I'd have still won. And then you can see that Johnson & Johnson, the blue line, was not very volatile, but it didn't perform that well. And then the brown line is what you would do, what performance you would see if you had invested an equal amount in each stock at the beginning of 2012. Another way to look at the same data is with this scatter plot, and this is going to be useful in a Markowitz portfolio model. So what we're seeing is a measure of volatility or risk on the x-axis. The farther to the right you go, the more volatile, the more risky, if you will, that stock is. On the y-axis, we have that measure of mean return. The higher the point is on the y-axis, the better performing the stock is. So sure enough, Bank of America is on the top right-hand corner. If I hover over there, hover over that point, I see more of that interactivity in Bokeh plots. I see the symbol Bank of America, and I have the actual values of volatility and return. And sure enough, it's both the most volatile and the best performing stock. And then I can zoom in on this cloud, and I can see I can better get an idea of the relative performance of the various stocks in that center there. So again, that's another way to look at the same data. And I got this with 9 lines of Python in the bokeh system, including this ability to hover over the points and get that custom information. That's what line 3 gives me, is this hover tool. So really powerful stuff bokeh provides, and pandas too, of course. Now it's time though for the big guns. If we're going to do optimal portfolios, we need Gurobi. So to recap, we have a quadratic programming model. I'm going to minimize risk, which is a quadratic function of the portfolio allocations, subject to a fixed budget. We're going to invest $1 in our portfolio. We don't want to take a whole lot of risk here. Okay, maybe $1 million, whatever units you choose here, but we're going to do that. Subject to a fixed return. We're going to specify the exact return we want to hit, and we want the minimum risk portfolio that gives us that target return. And then we're going to require that the amount of money we put in each stock is non-negative. For those of you who have done trading, you may be aware of shorting, which involves selling stock that you don't own. That's equivalent to investing a negative amount in that stock. We're not going to do that here for simplicity's sake. We're going to require a non-negative, possibly 0, but non-negative investment in every stock. Now, in order to build this model, we do need one more matrix. We need that covariance matrix sigma, and that requires taking each pair of stocks and all of its performance data and computing a correlation for each of those pairs. And thankfully, pandas can do this in a single line. And that's what we've got right here. So that's this 30 by 30 matrix, again with nice column and row headings that pandas provide, so I know exactly what I'm looking at. And let me zoom in on a small subset of this matrix here. This is Cisco and Walmart, and what we see is that they're negatively correlated. The top right and the bottom left show a negative value. What that means is that when Cisco rises, in all likelihood, Walmart fell, and vice versa. Now, of course, this is a statistical thing. Sometimes they both rose, and sometimes they both fell. But on average, Walmart and Cisco are negatively correlated. And the Markowitz portfolio models take advantage of correlations like this to improve the risk performance of portfolios. So this is critical information if you're doing Markowitz portfolio theory. So it's time to build our optimization model. And so we need to follow those 6 steps, step 0 being to import the Gurobi-Python module, and then instantiating our model. And then we need to create one variable for each stock. And that's what we were doing in line 8, but we're doing something kind of different here. I've decided to stuff these variables inside of Pandas data frame. Hopefully you can tell by now I'm a big fan of Pandas, but what I found is that using Gurobi and Pandas together gives me some pretty nice dividends that may have been unexpected. So we'll do that here, and again we see we have a single column data frame, and on each we've got the row headers tell us what stock we're dealing with, and in this column each of the Gurobi variables has been placed inside the data frame. Now why do we do that? We did that because now I can use the various Pandas computational routines to compute the key quantities in my optimization portfolio. So that's what we've done here with 3 different Pandas calls. We're computing my total budget as a linear expression of my portfolio allocation, the mean return, which is a dot product between my average return vector and the allocations themselves, and then the risk, which is a double dot product, or it's a quadratic function. So when I execute this, then I can look at the values here, and you'll see that the total is just the sum of my allocations. That's pretty straightforward. And the return is a weighted sum where the weights are taken from the average return of each stock. And then the risk, which is a quadratic function. Every possible product between the 2 stocks is represented here. So that's a bit complex. But the point is I did that in one line of Pandas. Again, I just love having these powerful data analysis tools at my fingertips when I'm building models. Saves me a lot of time. So now we've built those expressions. We can set our objective function, which is to minimize risk. We're going to add our budget constraint. So our total budget equals 1. I didn't use I could have done this instead. Let's go ahead and do that. Why not? We can use this instead to specify that our total budget equals 1. And then we've also set a parameter that specifies I'd like to use a simplex algorithm. I like using the simplex algorithm when I really want a vertex solution. And so that's a technical feature of the simplex algorithm that is helpful for me in this portfolio design process. So let's start building some optimal models. So what we haven't done yet is set our target return. What target return would we like? But let's as a first step, let's solve our model without that target return set. What that's going to give us is the minimum risk portfolio without regard to return at all. In other words, no matter what the return is, if I have to invest $1 in the stock market, where's the best place for me to put it in terms of risk, minimizing risk? So Gurobi solves it in 13 iterations and in 1/100th of a second. What I've done here in line 3 is to extract the numeric values of each of the stock allocations, and I've put that in a new column of my pandas data frame. And I've titled that column minimum risk. So now I look at my data frame, and again, my first column is the variables, and actually Gurobi's conveniently given me the numeric values when it prints out, and then the minimum risk portfolio in the second column, and you can see it's a mixture, a variety of different stocks, although there are quite a few that are completely removed from the portfolio. Now let's go ahead and set a return target. What I'd like to do is set a target so that we're getting 50% of the mean return that Bank of America got, but we'd like the minimum risk portfolio that achieves that 50% return. So lines 2 and 3 do that. What I do is I've extracted the maximum mean return from my extremes data frame, multiply by 0.5, and then I set my fixed return, my constraint to be that return is equal, that my return is equal to that RET 50 value. And then I'm adding that constraint to the model. And I'm giving that constraint a name, fixed return, for reasons which we'll soon see. Then I'm going to go ahead and optimize and extract the values of my portfolio allocations, put them in another column on my data frame, and then while I'm at it, I'm going to go ahead and create a third column for the maximizing portfolio, which is put all the money into Bank of America and put nothing everywhere else. So again, I solved that. Gurobi solved it so fast it didn't even tell me how much time it took. That's probably because it was able to use all the previous work that it did. You'll note that all I did was add a constraint to my existing model. I did not have to build a new model from scratch. When I've done that, I get a portfolio. It's a fair amount of investment in Bank of America, but I also have Home Depot and Walmart and a couple of other stocks. So let's plot these results by looking at those 3 different portfolios. Oops. Sorry about that, you guys. Let me go over here. Let me go back down. So let's plot those 3 portfolios. When we do that, what we see is that our blue line is the Bank of America roller coaster that we looked at before, followed by in the green line, which is the 50% target portfolio. And sure enough, on a logarithmic plot, it looks like, and that's the scale that these models work in, we're getting about 50% of Bank of America's performance. And then our minimum risk portfolio, which did rise some, but didn't get great performance, but you can see that it's not very volatile at all. So we were able to construct those 3 portfolios rather simply. But you know, we're not really interested in just 3 portfolios. What we like to do is look at the entire trade-off between risk and return. That is to say, at any given target return value, what is the minimum risk portfolio? And to do that, we need to solve a lot of models. In this case, we're going to solve 101 models, all the way from Hewlett-Packard, the worst performing target return, to Bank of America, the highest performing target return. And we're going to run Gurobi 101 times. Now, if we look at the code here in lines 13 through 17 is that loop. And what we're doing, all that we need to do here is change the right-hand side of our return target constraint, which I named fixed return. You may recall in the previous cell. And so I've not modified the model at all. I didn't have to reconstruct it. All I've done is change the right-hand side, and then I rerun the optimize command. Gurobi takes advantage of all the previous initialization it's done, and as a result, all 101 models are solved in less than a second. I reran this whole model for you at the beginning of our seminar, so I'm not going to do it again, but it runs really quickly now. And then when we plot these results using bokeh once again, I'm applying a couple of tricks here so that I can differentiate between returns that are better than the minimum risk value and returns that are worse than the minimum risk value. I get what we call the bullet. This is a common feature of any Markowitz portfolio trade-off, is this bullet shape where the worst performing stock, Hewlett-Packard, is at one end of the bullet, and the best performing stock, Bank of America, is at the other end of the bullet. But every point on this bullet shape is a portfolio on what they call the efficient frontier, or the Pareto optimal design, or the Markowitz optimal portfolio curve. And what these are these are the portfolios that achieve either the best return for a given level of risk, or alternatively, the other way to look at it, is the lowest risk for a given level of return. So let me zoom in a little bit for you, and we'll show you a couple of things. So for example, Johnson & Johnson right here, I don't have that hover tool in this particular version of the plot, but Johnson & Johnson gets a nice low risk, but we can get the same return at much lower risk with a mixture of stocks. On the other hand, Home Depot, we can look at Home Depot, it gives a better return than Johnson & Johnson, of course, at more risk, but we can actually improve the return without any additional risk over that individual Home Depot stock. And so what we find is that the Markowitz stocks do better than any individual stock in the portfolio, whether you look at it on a risk basis or a return basis. And we did all this again in 150 lines or so of Python using Gurobi and Bokeh and Pandas in this interactive notebook. So let's drop back to the presentation. And we've got some closing thoughts. First of all, let's talk about developers and analysts and their collaboration. We think that analysts, people who prefer working in the mathematics and less in the development, are going to greatly prefer Jupyter. They're going to love it because it gives you this interactive, iterative development style and these self-documenting notebooks that combine the code that they've tried and the results they've obtained and any visualizations that support their work and documentation. On the other hand, developers might benefit from more traditional IDEs like Spyder. And the graphical debugging and the documentation browsing and so forth that a traditional IDE provides. But what's nice about that is that we don't have to force either one of them into an environment they're not comfortable with. They can collaborate relatively easily here. In fact, what I propose is that an analyst would build their notebook, and when they're happy with the results, the code that they have built is Python, ready to be inserted into standard Python modules. In fact, in my personal development style, I use IPython for just that purpose. I use Jupyter notebooks to prototype my code, and when I'm satisfied with the results, I copy and paste that code into standard Python modules and import those modules back into Python, back into Jupyter rather, so I can verify that they're working as I expect. And so both of these are completely valid ways to interact in Python, and hopefully it helps you understand how analysts and developers can collaborate more effectively because they're both working in the same Python ecosystem. So finally, to wrap up, here's what we've looked at today. First, we looked at the Gurobi-Python interface, and it brings the expressive power of a modeling language into the Python ecosystem. So now we don't have to pick between a programming language and a modeling language. We get both within Python thanks to Gurobi's Python interface. We looked at Spyder, which offers a traditional IDE for Python development, including full-featured editing and graphical debugging. We looked at IPython and the Jupyter Notebook system, and I think this is an incredibly powerful paradigm for me, and I hope it is for everyone here, for interactive development, collaboration, and sharing. And then there's, of course, the Anaconda platform behind all of this, which delivers a suite of powerful open source tools powered by Python and the ability to connect to world-class commercial software like Gurobi. Now, of course, if you need any additional assistance, whether it's training, enterprise support, consulting, we at Continuum are happy to help you and work with all of these packages.
Thank you to our presenters today, and thank you all for joining us for this webinar. Remember to go to gurobi.com/get-anaconda to download a copy of Anaconda and Gurobi for your own system so you can try them for yourself. Have a great rest of the day.